Scientists found a new method to detect exoplanets. The simplest way to explain an exoplanet is that in our solar system, every planet revolves around the Sun in our solar system. Exoplanets are planets that revolve around other stars. The term exoplanets refers to planets outside of our solar system. Exoplanets are extremely difficult to observe using telescopes directly. The intense light from the stars they orbit obscures them. Therefore, astronomers employ various techniques to find and research these far-off planets. I invite you to another innovative video from Theory of Science. Today, we'll talk about the cutting-edge technology that researchers use to find exoplanets. The exoplanets range in size from small, rocky planets approximately the size of Earth or Mars to gas giants bigger than Jupiter. They may be frozen solid or hot enough to cook metal. They are able to orbit two suns simultaneously and can orbit their stars so closely that a year only lasts a few days. Some exoplanets wander the cosmos in constant darkness. Multiple exoplanets have been discovered around single or normal stars, but others have been discovered in binary or triple star systems and around stars of more unusual types. Exoplanet discovery can be accomplished using a variety of methods. Each method is usually vulnerable to different kinds of planets. Direct imaging and observation of transiting exoplanets have had the most effects on the characterization of atmospheres. The Autonomous University of Nouveau Lyon, UANL, and New York University Abu Dhabi researchers proposed a fresh method for spotting faint entities revolving around unusual binary stars known as cataclysmic variables, CVs. This has been presented in research published in the monthly notices of the Royal Astronomical Society, MNRAS. Now, what are cataclysmic variables or CVs? They are a pair of stars so close to one another that one star absorbs material from the other. The brightness of the pair changes drastically due to their close proximity, which causes the second star to fade. As part of the study, the researchers analyzed the variations in the brightness of four CVs: Lu Camelopardalis, QZ Serpentis, V1007 Hercules, and BK Linces. CVs see significant brightness improvements. Even our own sun varies in brightness to some extent among the stars. However, CVs have an erratic increase in brightness that is far more pronounced than that of stars like our Sun. Cataclysmic variables come in a variety of forms, including classical novae, dwarf novae, certain supernovae, and others. All types use the same fundamental mechanism. One star is more massive than the other in a pair that closely orbits each other. Astronomers refer to the lower mass star as the donor star, while the more massive one is known as the primary star and takes gas from it. In a CV, the donor star is typically a red dwarf, whereas the primary star is a white dwarf. Compared to white dwarfs, red dwarf stars are both colder and less massive. Their radius is roughly 20% that of the Sun, and their masses range from 0.07 to 0.30 solar masses, while white dwarf stars have a typical mass of around 0.75 solar masses and a very small radius similar to that of planet Earth. The new method is based on changes in brightness in the accretion disk. An accretion disk is created around the primary star when the material is drawn in from the donor star. This disk is where most of a CV system's brightness originates, outshining the light from the two stars. The accretion disk's material heats up, which increases brightness. The increase has the potential to overwhelm the light from the two stars. Dr. Carlos Chavez, a researcher from Mexico's Universidad Autónoma de Nuevo León, is the study's principal investigator. Testing the third body hypothesis in the CVs, Lu Camelopardalis, QZ Serpentis, V1007 Hercules, and BK Linces was necessary. The updates appeared in the Royal Astronomical Monthly Notices, where Chavez is the paper's primary author. The four CVs' brightness changes have been measured by the researchers. The distances and masses of potential third bodies in the systems, based on the brightness changes in each system, have been estimated using this. The intrinsic shift in luminosity that may be seen from various perspectives is the foundation of the investigation. The study illustrates how planets might live in erratic surroundings orbiting CVs, and describe how astronomers can find them. Our work has proven that a third body can perturb a cataclysmic variable in such a way that can induce changes in brightness in the system. These perturbations can explain both the very long periods that have been observed between 42 and 265 days and the amplitude of those changes in brightness. According to the team, 2 of the 4 CVs that the scientists examined contain bodies resembling planets orbiting them. Very long photometric periods, VLPPS, which are times of increased luminosity that don't match the orbital periods of the binary, are present in the 4 CVs. The L1 point, also known as the Lagrangian point, is situated between the 2 stars and the third body. It is a location where the gravitational pull of the stars is balanced. The dynamic L1 point moves in relation to the motion of the stars. In a previous article, the lead author, Chavez, demonstrated how a planet, a third body, might generate oscillations in the L1 point. The mass transfer rate, that is, the amount of matter sucked into the parent star, changes as the L1 point does. The brightness of the entire 3-body system changes when the mass transfer rate changes. The researchers think this is a viable new method for expanding the thousands of planets discovered over the past 3 decades by discovering planets in orbit around binary star systems. However, the approach Chavez and his associates created is independent of planetary transits. It is dependent on the inherent brightness change that may be seen from various perspectives. Do like, subscribe, and press the bell icon for more interesting future videos. Check out our channel for more interesting content like this.